is that the bigger the molecule is, the bigger B is going to be. All right. So, I mean, so like CH4 is a smaller molecule than acetate.
Why?
Or say it's much smaller than
Glucose.
DNA. Or glucose. Glucose is reasonable. Which C6H12O6. So, yeah.
Anyway, so what you need to remember is that the bigger the molecule is, the bigger
The bigger the adjustment.
the difference of the ideal is.
Tim,
The less ideal it is, the bigger the molecule.
Tim,
is.
how do you know if a molecule is big?
By this number of molecules. Oh, wait, are we talking about whole moles?
So Nathan just said methane, CH4, is bigger than, smaller than acetate, right? How do you know if it's smaller or bigger?
Because of the number of molecules.
Number of
Not necessarily number of molecules, but number of...
within one molecule. How do you know one molecule is bigger than another molecule? Usually there's more.
No, you're not wrong.
Oh, okay.
What are you... Just explain it better, okay?
Like, are you talking about like the size of atoms? Or
Yeah, like we're saying, so when we consider an ideal gas, the assumption we made earlier on was that it has no volume, right? Now here we're saying that if it deviates from the ideal, it has a significant volume, right? Or a more significant volume necessarily. So the idea is that the larger space the atom actually consumes, the more it deviates from the ideal. So you'll see that acetate deviates from the ideal gas more than methane would. And so Jack's showing you what the chemical structure is and how you can kind of predict that this is a lot bigger than that. Yeah. And in this case, a more significant example might be glucose, where you have a huge chain.
Yeah, like a big
Here we go.
H612.6.
Oh, you want?
I'm messing this up for you now, since you to make it more significant.
You had one job. No, I showed more than one job.
All right, but the point is that the molecule is bigger, and you can tell, but it has more atoms bonded to each other, and you can see that it has a greater mass, right? So two ways to tell: its mass is bigger, and it has more atoms inside of its inside one formula unit or one molecule.
Are those supposed to be H's?
Yeah.
Okay.
Are they not?
They look like W's.
Most of your H's always look like W's. We've been confused for the longest time. But we finally
Now it
figured
looks
out.
like a D. Okay, or a K.
I will work on this.
Yeah, there we
Beautiful.
go. Hilton style, right there.
Yes, it's bonding with tungsten.
All right. So the other idea is that there are attractive and repulsive forces between molecules. Right? There's these little forces that affect things, and you account for that in the van der Waals equation by subtracting n squared a over v.
Right. So I have attractive forces, but Nathan has repulsive forces.
Anyway,
It's
there's
just
just
the orange shirt.
just a bunch of little forces that actually do have an effect in real gases, right? And so A is once again a constant that is kind of made up based on the gas. And
So that'll vary on sample by sample.
A of CH4
Actually,
is also less than A of
it just varies by type of gas, right?
C6.
Well, if you had a sample that has like a mixture of gases, then
A also increases with the size of the molecule. So basically, the bigger your molecule is, the more it deviates in every single way from the ideal. Does that make sense? And your question was, if
Like,
like,
composition book.
what was that question on the UIL test? It's like, how do van der Waals forces affect intermolecular force or whatever? Just so we can make an example of that.
oh yeah,
Right.
Wait,
So,
so can we answer with
Yeah.
the knowledge you've given us now? Would we be able to answer?
nice. Yeah, Shazib's on something. All right, well,
He's on a chair.
I'll give you guys a question right here. The three of you and Ember has a question up here. So, where is it? 27. And Rishi, you can look behind you.
Okay.
So the three of you work together. Rishi, you can pause it if you want.